Hello, my name is Nathan Dunnigan, and this is my Physics 2212 Lab 3 magnetic field of a bar magnet. The purpose of this lab is to measure the distance dependence of the magnetic field due to the small bar magnet and compare the measurements to the distance dependence predicted by the equations for the on and off magnetic fields derived from the PHYS law. I will also simulate the magnetic field of the bar magnet using GlowScript, and to do this I will use a magnetometer app on my phone and several different distances r away from the magnet to do so. The first fundamental principle we will be using is the Biot-Savart law, which relates the magnetic field produced by an object at an observation point to the current I running through the object and the distance between the source of the field and the observation point r. The magnetic field dB for a section dl is the following equation derived by the Biot-Savart law in yellow. Then integrating the Biot-Savart law and looking at the limit where r is much greater than s, we get the following two equations for the magnitude of the magnetic field on axes and off axes. The final equation for the magnitude of the magnetic field of a bar is given in the lab to allow us to solve for n. Then we will also be using the general formula for the magnetic field of a dipole and the distance dependence equation given in the lab to solve for the constant n and k. Here is a visual representation from the lecture that I believe does a very nice job at showing the magnetic field produced by a bar magnet, which also shows how we can treat a bar magnet as a magnetic dipole, which is the main assumption we are making in this lab, in order to apply the Biot-Savart law. For a preview of my results, the magnitude of the net magnetic field increases as distance decreases. N equals negative 2.7868, mu equals 2.788 times m squared, and then there is a 9.33% difference between the experimental and computational model, which will be discussed later. For the experiment, the system is the observation point or the magnetometer, or the surroundings are the bar magnet, which produces the magnetic field, and the earth magnetic field. For the initial conditions, the bar magnet is placed at one end of the ruler and using a piece of tape to help determine the magnetometer on my phone. To determine the location of the magnetometer, my phone was slid perpendicular to the meter stick, positioned vertically and horizontally to find both maximum and minimum values for the x and y components. Now we will determine different distances between the bar magnet and the magnetometer that produces a magnetic field with specific x components for on-axis and a specific net field for the off-axis. The procedures for the on-axis experiment was to determine several different distances using the meter stick where there was a specific magnitude of the magnetic field in the x direction. And then for the off-axis experiment, we measured distances between the magnet and the magnetometer that the net magnetic field was 100 microtesla, and we recorded the y component of Earth's magnetic field to make it more accurate, and this is seen in the picture to the right with 2D perps and 1D. Now for the data analysis, you will see at the beginning the on-axis distances measured and the magnitude of the magnetic fields. And then in the bottom you see the off-axis field measurements, which is important to note that the corrected y component is found by subtracting the Earth's y component from the measured y component. And then finally, the graph shows a regression line, and the slope of the regression line is equal to n, and the y-intercept is equal to ln k. N is equal to negative 2.7868 from the linear regression equation, and then I solved k using Euler's constant and the exponential function, and then finally I was able to solve for the magnetic moment of a magnet, which is equal to 2.78a times m squared. The two correct statements given were that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, and that as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. And then I also noticed that the position of my phone is significant in ensuring that the magnetic field of Earth does not interfere. Now for my computational model, I started with the physical constants and creating the bar magnet, and then also defining the function of a magnetic field. I then went to creating scales for the arrows, creating the axes for each arrow, and then visualizing my on-axis magnetic fields that I calculated earlier. Next, I went on to visualizing my off-axis magnetic fields, which is seen in the code to the left, and then finally I visualized the magnetic field at the 45-degree angle off-axis using the d-perp from the experiment. And then finally you can see the visual that my computational model created, and then my answer, which shows all the b-axes and the off-axis perpendicular vectors, as well as my final answer. For the experimental versus computational model, the coding model uses exact values determined from the experiment, but the experimental magnitude from my measurements off-axis was 6.18 times 10 to the negative fifth, while the computational magnetic field was 5.63 times 10 to the negative fifth, which was a 9.33% difference. And then sources of error for my experimental model were that other electric devices near the phone, location of the magnometer may not have been exact, inconsistent placement of my phone during the experiment, and if the reading of the magnometer did not exactly match Earth's magnetic field prior to the experiment, my off-axis results may be inaccurate, which is why there might be a difference. For the first what-if question, the results would have been much less accurate as the x and y components would have been different, as the magnetic north from Earth's field would have affected both the x and y components. And then for the second what-if question, I would expect my magnitude to increase double actually due to superposition, but the direction to stay the same, and the measured distances may decrease due to increased magnetic field.